Off you go, friends.
Hi, everyone. So yes, as Neil mentioned, this is based on the feedback that we received last week about what topics people might find interesting to hear about. It's also an area that is one of the areas that I actually do work on and research on, and I've been thinking about these topics for a relatively long time. So feel free to ask any questions. We can make this more interactive. And I should also just say that these slides were from a much longer presentation. So towards the end of the slides, instead of deleting a lot of the content, I just moved them to the end of the slides. So some people, if you are interested in looking at some of that content, I have them later in the slides. I'm not sure if those are going to be useful just as slides without me speaking over them, but hopefully you will be able to follow them along if you're interested. So I struggled to come up with a short title for today because I'm talking about a bunch of related topics and people mean slightly different things by these different terms. So I could have called this unsupervised learning, which is probably what I would have called it, say 4 or 5 years ago. Nowadays, I think it's much more relevant to talk about transfer learning because it's a little bit more specific of an idea compared to unsupervised learning. And I also put representation learning here, which is a little bit too broad compared to what I want, what the scope of this presentation is going to be. So I will try to along the way explain what these different terms mean in the context that I was trying to put them together. But essentially what I'm interested in here is how we can use deep learning to learn useful representations of data that allow us to solve a bunch of different tasks involving a certain kind of data, for example, images or text. And the context, which is slightly different from what we have considered before, is that we are in the unsupervised setting. So unlike previously, where we assume that we have access to some input data X and some corresponding label or some desired output Y, and we were talking about pairs of X's and Y's, here we assume that we only have observations of this input data. So think about X1, X2 as, for example, images. And we typically assume, although this is not necessary, that these samples that we have been drawn independently and identically distributed from some underlying distribution PD. So with PD, I denote the distribution of data. That is the natural distribution of, say, images. And broadly speaking, the question in unsupervised learning is, can we learn something useful from this? So in supervised learning, we knew that our task is to predict some labels or predict some desired outputs. So the goal of learning was very clear. Here we kind of have to define that goal for ourselves. What is it that we want to actually do with this data set that we have? And I largely try to categorize unsupervised learning methods based on what it is that we're mathematically trying to extract from this data into two categories. In the first category, which is what I would say a lot of the community has focused on before the most recent deep learning hype cycle, so to speak, is that the goal, we define the goal of unsupervised learning as modeling some aspect of the data distribution. So for example, we want to come up with a parameterized probabilistic model P theta of X, which in some sense approximates the true distribution P data of X. And if you have such a model, that in itself is useful for many things. You can use it for compression. I don't know if you have studied information theory, but you might know that the better your model is of the distribution of some random data, the shorter or the more efficiently you can compress that data and store it. You can also use a probabilistic model like this for data reconstruction. So one of my favorite examples of this is trying to create that famous image of a black hole, which was the first image of a black hole, first have to know what a black hole is likely to look like. We need to have, if our method outputs a particular image, does it look like a black hole or does it not look like a black hole? So if you have a model P theta that, for example, you train on simulations of what, if we simulate what black holes might be, we can simulate what they would look like. From that, you can build up a probabilistic model. From a lot of samples of those simulations, we can build up a probabilistic model of what photos are likely to be pictures of black holes and what photos are unlikely to be pictures of black holes. And if you have that probabilistic model, now you can use it in conjunction with some measurements that you might have to reconstruct a particular picture of a black hole based on the measurements that you have. And finally, you can also, if you have a probabilistic model, you can take samples from it. And this is often called generative modeling or generation. So we've already seen this with the character RNN. You can train a character RNN on, say, Shakespeare, and then you can ask it to spit out random examples of text that looks like Shakespeare. This doesn't always have a very direct application because why would you want random text snippets of Shakespeare? But in some contexts, this might still be useful. So for example, in chatbots, if you want to generate some random looking or natural looking text conditioned on some data, you might be able to use these generative models to generate a sentence describing some answer. So this is one potential goal for unsupervised learning, is to learn a model of the distribution. Another possible goal of unsupervised learning is to learn a data representation. I show two ways of thinking about representations. It can either be a function g theta, which maybe we're typically going to consider this to be a neural network that takes, say, your image as input and it outputs a vector z. And for each image, you would have a different vector z. And or alternatively, you can make this stochastic. So instead of returning a single z for each image x, you might return a probability distribution over vectors or a sample from a probability distribution of vectors. So you can have random representations attached to each image. And why would we want to do this? We might want to do this because we believe that this z is somehow a more useful representation of our data in order to solve some, say, classification task further down the line, compared to, say, or if the z is sufficiently low dimensional and the coordinates are sufficiently meaningful, we might want to learn a representation of data in a vector space in order to use it for visualization. We might want to plot our data in 2D, even if it lives in very high dimensional spaces. And representation learning can enable that as well. I want to point out that these two I personally consider very different objectives, modeling the data distribution and somehow learning a good representation of the data. But this distinction is not very clearly made, or sometimes in the literature, people start out by building a good generative model in the first sense, trying to model the distribution of data, but then they look at, they extract a representation from it and pretend that this is what we wanted all along. And that's one of my personal things to make a very clear distinction about what the goal of the particular unsupervised learning algorithm is that I'm working with. So I'm going to first look into the first type of unsupervised learning methods, which is when we are trying to model distributions. I don't know if there are any questions in the chat. No, it's just
not so far. Just me apologizing for saying morning then afternoon, and linking to David Mackay on information theory and machine learning.
That's a great book. I also recommend to everyone. So yes, good afternoon, everyone, in case I also made the same mistake. So unsupervised learning as distribution modeling. The goal is to model the data distribution. Theta are generally some set of parameters. And one of the gold standards for trying to find the parameters for which this approximation holds is to find the maximum likelihood parameter. So we sum up the log probability of our of each of our data points, which is called the log likelihood of our data, and then we find that, and then we seek the parameters which maximize this quantity. We've seen this in the RNN example already. This is, by the way, not generally, so not every single unsupervised learning method will try to do this, but a very broad class of them can be understood as trying to at least approximate maximum likelihood training. Here is a list of various methods for how you can use deep learning for modeling distributions. I don't know why suddenly my maths became so small everywhere. Excuse me for that. So the first one is an example of which we have already seen with RNNs, are called autoregressive models. The key difficulty in modeling probability distributions is that in very high dimensions, if you want to work with probabilities, they have this property that they integrate or they sum to 1. So if you sum up the probabilities of all possible outcomes, they have to sum to 1. And when you have to sum over all possible possibilities in very high dimensional spaces, that sum becomes intractably difficult to calculate. And this is why modeling a probability distribution with a neural network or with any other function is generally very difficult in practice. And these, you can think of these as different approaches for making that still tractable. The first class is autoregressive, which makes this joint distribution tractable by decomposing it using the chain rule of probability distributions. So if this X was a sentence, it has capital T characters, then we have seen that the character RNN decomposes this as a product of the probabilities of the next character XT, given the sequence up until the T minus first character. And this equality always holds. And because now each of these terms in here requires you to define a distribution over a single character conditioned on others, you can tractably represent distributions of this form, because summing over all characters is significantly easier than summing over all possible sequences. And that approach can be also used in the context of images. We've seen the spatial LSTMs, but there are other autoregressive models for images and other types of data as well. The second kind of way to use neural networks to model distributions is via implicit distributions. So here you assume that that your data X is some nonlinear function g theta of an underlying representation or an underlying vector z, and you assume that the underlying vector z is sampled from some simple distribution, for example, a standard normal distribution. This is called an implicitly defined distribution because you don't specify the probability density function or probability distribution function. Instead, you define a process by which you can sample from this distribution. You would first sample a z from a Gaussian, and then you push it through this nonlinear mapping in order to obtain a sample in the space of where this X lives. And a very high-profile example of such models are generative adversarial networks. And of course, this is just very much a part of a story. The real story is how do you actually then train models that are defined in this form. And that's one of the ways you can train them is using the GAN approach. Another popular neural network models for densities or distributions are flow models. So these are sometimes called normalizing flows. And or volume preserving transformations, or non-volume preserving transformations, which is what the NVP stands for. This is essentially an implicit distribution, but with a special constraint on G that ensures that G is invertible, so that Z can be precisely reconstructed from X. And in addition to it being invertible, it's also a requirement that this inverse is computationally tractable. So it's easy to calculate this inverse, and it's easy to calculate the Jacobian of this transformation as well. And if these things hold, so this function G has a tractable inverse and a tractable Jacobian, then you can use efficient maximum likelihood training in these models. And finally, which is what I'm going to talk a little bit more about, you can model distributions with latent variable models. And I generally denote latent variable models, p theta of x, in this general form. So you define a distribution over observable variables x by defining a joint distribution between x and some unobserved hidden variables z. You can think of these z as, so if x are images, you can think of z as some latent variables such as the number of objects in an image, or the type of objects that are present in an image, or the orientation of the different objects in the image. And it's usually easier to define a joint distribution between an image and some hidden variables in a way that I'm going to talk about later. And in order to define a density model or a distribution model over the data, we have to marginalize over the various possible values of z. So this integration is the marginalization that needs to take place. Let me try to quickly, I don't know how to edit it from here. Anyway, I try to fix the small font size on my equations because it really makes it very difficult to see. So this is what latent variables are generally like. And to motivate why this is interesting to use in neural networks, with neural networks, I want to give a few motivations. But before I do that, I want to say that when we usually define this joint distribution between the observable x and the hidden z, we usually do this by decomposing it as a prior over the hidden variables and what is sometimes called the observation model, which is what is the probability distribution of the images of the image conditioned on the values of the hidden parameters. And typically this may be something that's easier to model. So once you know what, say, if you're doing this very literally, and if z is really the number of objects and the type of objects and the orientation of objects, it's usually easier to model this distribution once you know the values of z. So once you know that there are three objects, each of them a different kind of dog in certain orientations in the image, it may be a lot easier to model what the image should look like if these are the values of the underlying hidden variables. The first motivation for why we like to use latent variable models is that it makes sense. So this is I think the most hand-wavy way of putting this. It describes data in terms of a generative process, which is that there are some underlying variables out there. So for example, object properties or locations, and that really what we see, what reaches our retina or what our camera captures is just something that is a representation, a pixel by pixel representation of those underlying hidden variables. So we kind of imagine that these underlying latent variables z to be some kind of interpretable, to have some kind of real world corresponding meaning. And it is sometimes the case, or often the case, that the latent variables that we learn, we can often, after the fact, attach some interpretation to them. That one coordinate of z might have learned the number of goats in the image, and the other coordinate of z might have learned the position of the sun. And the two of them gives you a particular image with a particular lighting condition. And then finally, it makes sense in the sense that if you want to reason about causal relationships between these different unobserved properties of your data, so for example, you want to reason about what's the probability of seeing a cow in a factory or something like that, then usually that causal reasoning about data needs some sort of latent variables. You usually cannot express these causal inferences without reasoning about some latent variables in addition to the data or the coordinates that you can observe. The second motivation, which is often what the deep learning community would talk about, is the manifold assumption. And here, think about images, for example. Think about a 100 by 100 image with 3 color channels. If you represent that as a vector, that is a 30,000 dimensional, if I calculated that correctly, a 30,000 dimensional vector. But if you just take an arbitrary 30,000 dimensional vector, you can display it as an image, but it's very likely that it's not going to be anything that's a natural looking image or anything that is an image that you would encounter in the real world. So in reality, if you consider all the natural images photos that you can take with a camera, for example, they don't occupy all this 30,000 dimensional space. In fact, most of the 30,000 dimensional space are not images. And what we usually assume is that the vectors that actually correspond to images are concentrated along some low dimensional manifold embedded within this high dimensional space. A low dimensional manifold, you can think about it as a nonlinear subspace, something that is, so for example, in a 3-dimensional space, the surface of a ball would be a manifold. That's an example of a manifold. So you can think about the generalization of this in a 30,000 dimensional space. Images might live on a couple 100-dimensional nonlinear manifold. And in this view, we can interpret this representation vector z, or hidden variable z, as some kind of intrinsic coordinates that tell you not where you are in the 30,000 dimensional space, which is what x tells you, but where you are on this specific manifold, which contains all the natural images that you can possibly take with your camera. So that's the second motivation that's usually given. The third motivation, which is very practical, is that latent variable models are a great way to combine very simple components to model something that is very, very complicated and difficult and elaborate. So an example here is that if we can choose the prior over latent variables to be very simple, and we can choose this likelihood model also to be very simple, and even if these two things are very simple, by simple I mean, say, analytically tractable or easy to work with, even if these two objects are simple, when you combine them in this fashion, the resulting distribution over data, p theta of x, can be very, very complicated. And a particular example of variational autoencoders, which I believe, having looked at the curriculum of some of your courses, I think you have come across VAEs maybe in the past. But if not, there will be links in the notes. In the variational autoencoders, we define a latent variable model where both the prior over z is a Gaussian distribution, and the observation model, which is the distribution of the image conditioned on the hidden variable z, is also a Gaussian distribution. And Gaussian distributions are just about the simplest distributions you can come up with. And the only where the complexity comes in is that the way you define the mean and the variance of these Gaussian distributions is via a nonlinear neural network. So these mu theta and sigma theta here can hide a multi-layer neural network that can be very, complex and complicated. But other than that, both of these distributions are rather simple and easy to work with. Yet when you carry out this integral, the resulting distribution in data space is going to be a highly nonlinear and highly complex distribution. And I'm going to jump forward to this to show that this is an image taken from the variational one of the variational autoencoder papers. It shows that if you up here we have Z space, which is the space where these representation vectors Z live. They are sampled from a prior distribution, which is very simple, and that is shown by this nice circle here. So that's a cartoon illustration of a Gaussian distribution. But when you take this, you sample one of these representation vectors and you want to sample what a corresponding image looks like, you would pass it through this decoder, and this decoder network might map it somewhere in image space. So this is the space of images down here. And for different values of Z, you might map it to completely different parts of the image space. So in aggregate, if you look at what images you would generate with this model, you're looking at this very complicated, manifold-y looking thing here, which is of course a cartoon illustration of what this distribution might look like in image space. And then a final motivation here, which is another practical motivation, is that in latent variable models, there is a very appealing framework for efficiently doing two things. So you want to do generally two things in a latent variable model. You want to be able to evaluate the probability of a particular observed data point, which is called the likelihood. And if you are doing maximum likelihood learning, then you typically want to maximize the likelihood of the observed data. But evaluating this is very hard in a latent variable model. The second thing that you might want to do with a latent variable model is to infer the representation Z from the observed image. And this is this posterior distribution P of Z given X. And in an arbitrary latent variable model, this is also generally very hard. And this is called inference, this step here. So both learning and inference is very hard, but the variational framework, which if you haven't seen, you just consider it magic, makes it possible to do approximate learning and approximate inference in essentially the same framework. So it allows you to approximate both of these steps. And if you do those approximations with neural networks, those approximations tend to be relatively good as well. So that is a framework that applies to almost any latent variable model that you can come up with. And this is why latent variable models are very often used for unsupervised learning. And so to conclude, this is now a rather old illustration of the representation that you can learn with a variational autoencoder, which is one example of these latent variable models. What you're looking at here is on the left-hand side, you see the same face, which was generated by a variational autoencoder. So this face was generated by taking a vector in Z space and then passing it through the decoder network, which generates something that can be displayed as an image. And this is what it looks like. It looks like a nice, although a little bit blurry face. And what's happened here is that researchers have then looked at what the different dimensions in Z space correspond to in terms of interpretable features that might be useful features to have learned about faces. And they identified this particular dimension in which if you change Z along that dimension, so I keep incrementing Z along a particular dimension in space, and then I reconstruct the faces for those incremented versions of Z, I get the same face, which is roughly the same person, but with an increasing smile. So that's what you see at the top. And if I move in the opposite direction, so instead of moving in that direction in space and decoding, I move in the exact opposite direction in Z space and then decode, I get these very sad faces. And so this dimension in Z space has been identified as the smile vector. So this is a component of Z that is responsible for representing whether a person is smiling or not on an image that it encodes. And you can imagine that this is just one of the coordinates or one of the features that Z encodes. There are other things like hairstyle potentially, or maybe different aspects of gender or eye color and things like that, which may correspond to the biggest or most interesting factors of variation in the data that this model was trained on. So that's about the probabilistic unsupervised learning part. Now I want to talk about a almost completely different approach to learning representations from unsupervised data, which is, I would say, much more deep learning motivated, and it's also been much more successful in recent years, several years now, in learning useful representations from data. And this is generally described as self-supervised learning. I'm going to pause and look at the chat if there is anything people have asked.
Just me mentioning density networks is a very old example of the latent variable model. That, I think.
Yeah, I'm surprised you're not talking about Gaussian process latent variable models.
Well, I would be, but really they were inspired by David Mackay's density networks. So, he was the one that got me into doing what Ferenc is saying with Gaussian processes, because I sat in his group meetings back in 1997. And so that was like, I think it's, to my knowledge, it's the first time people did something like that, a neural network with a latent space on it.
Yeah, so I should say that a lot of the things here are not new. I think there is renewed interest in the idea, and then obviously better tools to make these representation learning techniques work much better, and also much bigger benchmark data sets where you can demonstrate the usefulness of these techniques on problems that people seem to care about.
That's really key. I think that one of the things, so with the techniques that I do this with, we don't get so impressive results because we're using very small data sets. But of course, no one knows that when they see the results, right? So, these results on enormous data sets are very impressive, I think. And, of course, they've already done the data set. And I think that's very interesting. And we see that being extended up to, say, things like GPT-3 as well, right? Once you've trained on that, it's kind of really impressive. I mean, it's perhaps less impressive from a machine learning point of view that you can do that if you train on all text data that's available. But, I don't know. I sometimes don't know what to make of it. I don't know what you think, Ferenc.
Yeah, so I think a lot of the emphasis with representation learning in deep learning is much more on how do you design a method that does not saturate with incredibly large amounts of data. So previously, I read yesterday there was a reading group that I participated in where we read an old paper from 1999, and even that was using a data set with like 57 examples in something like 80-dimensional space. So it was, by today's standards, that doesn't even pass as a toy example. But that's what we used to do back in the days. And nowadays, the interesting question is, if you can keep giving these methods terabytes and terabytes or even more of data, what method will allow you to continue learning useful information from it without the performance eventually plateauing once you reach a certain, once you reach a certain size of data set. And I think that's the main shift in focus, is that a lot of the more classical approaches to latent variable modeling do have these saturation properties. So it doesn't, they just stop improving once you reach their limits of what they can model. Whereas these super large neural network-based methods continue improving if you train them for very long periods of time on lots of data. I think, I don't know, that's my perspective on.
I think that's right, yeah.
On this. So with self-supervised learning, the basic idea here is that because neural networks are nice and modular, it's very easy to take a representation that you learned on one task and immediately use it in another task. So you can imagine that you have, say, a multi-layer neural network that you train to do some tasks, say, classify ImageNet, and then you can take that trained network, you can chop the head off, so which means that take the layers that are closest to the ImageNet classification output, because those are probably very specific to ImageNet, and just take the bottom of the network and then use it in a new application. You put another few layers on top of that network, and then you can now you have a neural network that has been pre-trained on ImageNet that extracts the same features that were useful for ImageNet, and you can hope that those features that you've extracted from ImageNet will help you solve whatever image classification problem you might have, classifying, plants or something like that. So this is what's generally called transfer learning in deep learning, which is when you train a neural network on one task, extract some parts of that neural network, and make it part of a new neural network on a different task. And then you can do this in various ways. You can either pre-train on one task, keep the network fixed, and retrain and then only train the additional parts that you've added on top, for example. Or you can use the network that you pre-trained on the first task as initialization for solving the second task, and then you continue training those layers of the network that you've extracted from the previous task. Sorry, I think this would have been way easier to explain if I had good pictures for this, but I don't have good figures to illustrate these points. The basic idea in self-supervised learning is that you first, if you have your unsupervised data, which is data without labels, you turn that unsupervised data into a supervised data set, by which I mean is that you take your data points xi and you somehow artificially create data that looks like it has input and output pairs. I'm going to give you examples of what this looks like. And so now you've artificially created a supervised learning task from your unsupervised data set. The easiest thing to imagine is, for example, if I have an image, I might want to predict one side of the image from the other side of the image. That would be one supervised learning task that I might want to create. So this task that I create in the first step is called the auxiliary or pretext task. Then I train a neural network to solve this auxiliary task. I don't actually want to solve this in practice. This is just there for me to exploit any statistical information that's in my data set. Once I trained on the auxiliary task, I take whatever representation I learned, which allowed me to solve this task, and I transfer it to some downstream classification task. So self-supervised learning is this two-step process. You define this pretext task, which is an auxiliary task that you don't really want to solve. You only create it in order to exploit your unsupervised data in some way. And then once you train the representation to solve that task, you then transfer that representation onto a downstream task. So here's an example which finally has pictures, hopefully makes things a lot better, which is one of my favorite examples to talk about. So imagine that you have a whole bunch of images. This is in an unsupervised setting, so absolutely no labels whatsoever. What I'm going to do is I'm going to take each image and I'm going to extract this 3x3 grid of image patches from them. These are non-overlapping image patches. And then I'm going to scramble the order in which they appeared. So this is called learning representations by solving jigsaw puzzles, because you can think of them as you're turning the image into a jigsaw puzzle problem. So you extract these 9 jigsaw puzzle pieces, you shuffle them, and then you train a neural network that can unshuffle it, that can predict what the permutation operation is that will take these shuffled puzzle pieces and reconstruct the original order or the original composition in which these puzzle pieces appeared in the original image. And the way it does it is that you have to first learn this network first has a feature extractor that turns, or a representation network that takes each of these image patches and turns it into a vector representation. So after that feature extractor network, you end up with 9 feature vectors for each of these puzzle pieces. And then on top of that, there is a classifier network that takes your 9 representation vectors concatenated, and then predicts the permutation that was applied when you shuffled the data. And of course, in between 9 puzzle pieces, there are a whole lot of different permutations that you can possibly predict. So this is a high dimensional or multi-class classification problem. But the idea here is that the feature extractor that you learn, which allows you to then predict how to unshuffle your puzzle pieces, has to be a useful enough feature representation for the network to be able to solve this task. So it has to understand roughly what parts a car has and how those parts of a car relate to one another in order to figure out that this is probably a wheel, and therefore it probably goes to one of the bottom slots. So it's the sort of reasoning that the network needs to learn. And it is only able to learn this by learning a feature representation that captures presumably some important aspects of the images. This is the pretext task. You don't actually want to train a neural network to solve puzzles. What you want is the feature extractor network. So once you train this network and it's able to reconstruct figures from these puzzle pieces, then you take that feature extractor network and then you use it in whatever image recognition task you might want to solve. For example, in image segmentation or car classification or whatever it might be. It's useful to think about how do we know if our self-supervised representation learning method works well. We can evaluate them in various ways. So here is the most usual way to evaluate is to look at data efficiency in the downstream classification task. So let's say that you do your self-supervised learning because you want to be able to solve ImageNet, or do well on classifying ImageNet examples with as few labeled examples as you can. So we have with red here a ResNet residual network, which was trained on raw pixels. And on the x-axis, you see the percentage of labeled training examples that this ResNet saw during training. And you can see that if you train on only 1% of the training data, the performance is really poor. And if you train with 50% or 100% of ImageNet, then obviously you get the best performance. The blue curve shows a ResNet, which was where you first solve a self-supervised task. In this case, this is contrastive predictive coding is the name of the pretext task. You take this feature extractor and then you train your ResNet on top of those previously extracted. And you can see that, the pretext task, the CPC task, doesn't have access to labels, so it only uses unlabeled images as input. And you can see that once you have this feature extractor trained, with only 1% of the ImageNet labels, you can achieve close to 80% top 5 classification accuracy, which is pretty good. In order to achieve this, training a neural network completely from scratch, you previously needed to use something like 5-7% of all the labels. And you can kind of see how favorably pre-training first on this self-supervised task compares to training directly on Scratch for ImageNet.
Friends, we've got a couple of questions.
Yeah.
So I'm just mindful of it being 8 minutes before, so I don't know if it's a good time, but I just wanted to drop that in.
Sure.
So Charles's question. Charles, do you want to unmute and ask your question?
Oh, sure. So I was wondering before in the case about the generating expressions by sort of tinkering with the like making up some random vector of z and then changing to see how it influences the final outcome.
Mm-hmm.
It seemed like it was sort of this core assumption that making one adjustment to one dimension has this beautiful correspondence to a very human readable format.
Yeah.
Which kind of goes against like this core sort of deep learning type thing where nothing really has any, you have to sort of let go of any sort of human representable data because it's all blown up into.
That's a very good question. I think this is generally the question you're asking is it's sometimes described as disentangled representations, where each coordinate of the z will correspond to like a different factor of variation in the data, and or each coordinate of z might be independently meaningful to humans. So just, I don't think that this is just one coordinate of z. I might have described it in that way, but I think here you are looking at a vector direction in z. So the only thing that's true here is that if you're linearly moving z along a particular straight line, this is the kind of effect you're seeing, but it's not aligned with the coordinates of z. So you have to change multiple coordinates of z to get this type of effect. There's a lot of additional work in how do you enforce z to be more disentangled, which means that one coordinate should correspond to 1 degree of variation or something along those lines. And there are various methods that try to enforce that. In the variational autoencoder, because you assume z to be marginally Gaussian distributed, that distribution is rotationally invariant. So, you know, any rotation of z of the latent space is going to give you exactly the same latent. Technically, is going to give you the same same objective function value. So you can't really identify, you can't really axis align these latent representations so that each axis will be something meaningful. But this is an entire field of trying to tweak these objective functions and learning procedures so that you get representations that are more and more disentangled. The difficulty here is that it's very hard to say what exactly a disentangled representation is without referencing something like a factor of variation that's meaningful for a human when we look at it. So it often ends up very subjective of, you know, in some data sets, we know what factors of variation exist. And so we can check whether we recovered those in independent latent variables. But in more unconstrained situations like an, you know, ImageNet or faces, we can only subjectively judge how good the independent latent variables are that we extract.
We have another question from Gabriele. I mean, I could either read it out, or Gabriele, you can unmute and ask if you're happy to.
No, it was more of a suggestion in the sense that maybe the way, how can we extract this? And I was thinking maybe we can find sort of like label certain images and then find the line which is most correlated with it. And then the second suggestion, which I'm not sure whether it makes sense, is since we are making this assumption that the covariance matrix is a diagonal matrix, does that maybe create some of these disentanglements or not?
So I think for the first part, yes. So sometimes, as I said, in some data sets, you do have some, like in the CelebA data set, the celebrity faces, which is what I think this was trained on, it is actually annotated with these different factors of variation. And so you can kind of check whether your extracted latent variables line up with those things that people have annotated before. The second question of whether the axis-aligned covariance matrix or isotropic covariance matrix for Z, which is here, not sure where this one, is responsible for this disentanglement. I think it's quite the opposite in a way, because as I said previously, because this is a Gaussian distribution, it's also spherically symmetric. So any rotation in latent space would leave this distribution completely unchanged. You can kind of check this. So one way to ensure more disentanglement is to replace this normal distribution with something that is no longer spherically symmetric. So something like a Laplace, coordinate-wise Laplace distribution or something like that. And that's done in independent components analysis, for example, and it's nonlinear variance. And that will try to align the factors of variation more with specific coordinates in Z. But actually the Gaussian distribution is pretty useless for doing that alignment, because it's you can't learn that rotation. And if that rotation is important for you because you want to interpret individual coordinates, then you're not going to get that.
So just to clarify, the Gaussian is the unique independent distribution that is rotationally invariant. So it's only Gaussians that this is true for. If you use anything multivariate non-Gaussian that's independent across the latent dimensions, they won't be rotationally invariant. So it's sort of it's funny that we choose Gaussians, but there's lots of good computational reasons for it. We're sort of a little bit at time. It was just getting quite interesting on the self-supervised, but are you happy to pause it there, Ferenc?
Yeah,
sure. Do you want to go, I don't know if you wanted to mention what's going on in this slide.
Yeah, so what I wanted to mention, very like one line, is that sometimes these methods are so powerful that you don't even need to learn any nonlinear things afterwards. So we extract these nonlinear feature extractors with SimCLR, which was one of the big methods. Then afterwards, you can just stick a linear layer on top of it and solve ImageNet with just a single linear layer on top of these. So that's an even stronger evaluation of these representation learning techniques, is whether it renders the downstream classification task solvable with just essentially a linear classifier layer. And this is also possible. So that's, I think I will stop here and take any more questions if people want to stay on and ask questions.
Brilliant, Ferenc. So yeah, if there are other questions, I'm going to stop the recording there. I can put Gabriele and Charles your questions up on the record.